Welcome back to Calculus 1. In this lecture, we're going to build off of what we introduced in the introduction to calculus, the concept of a limit through answering the tangent line problem. And we're going to introduce what the limit of a function is in this lecture. All right, so I wanted you to think back to the introduction. Ideally, you watched that right before this, or maybe earlier, so that way you had time to let it sink in. And we're looking at a problem called finding the tangent line to the graph of a function. It's a very concrete geometrical graphical problem. And how we approached it was not trying to answer finding the slope or equation of the tangent line, getting the answer right off from the start. We start by trying to get an approximate answer, which that was what we called the secant line. Now, in the graphs that we sketched, the secant line didn't necessarily always look close to the tangent line. So we let that second point get closer to the first, and we saw the secant line gets closer or approaches to the tangent line. All right, what we're going to get into in this lecture with the concept of a limit is making it more precise mathematically for what closer means. How do we mathematically let one point get closer to another? That's what we're going to define with a limit. Now, as soon as you hit the level of Calculus 1, the rest of mathematics beyond starts to become, very technical. There's a lot of definitions, especially if you go beyond the standard calculus sequence. Now, even though we're starting with Calc 1, your first really technical math course, we're not going to give a lot of definitions first. We're going to look at kind of some examples to motivate each idea like we are here. So let's jump straight to an example to kind of motivate what a limit is. All right, and the example is really simple. We're going to examine the values of this function, f of x equals x squared plus 1, a really simple function. And we're going to see what happens to the function values as the x values approach 0. All right, now in calculus, especially in the way I like to do my courses, I like to look at kind of every topic in kind of multiple ways. So what we're going to see in this lecture is a numerical and graphical approach to understanding limits. There is an algebraic approach, but that'll be what we kind of get to in the following lecture. So ideally, we'll look at things numerically, graphically, and algebraically in our course. So let's start with a numerical approach. We're basically just going to plug in repeatedly values of x that are getting gradually closer to, and we look at the problem here, we're asked to see what happens to the function values as x approaches 0. So we're going to plug in values of x that gradually get closer to 0. All right, this is straightforward. It's just plugging in basic concepts from pre-calculus. So let's pick just any values of x that will gradually get closer to 0. Let's start with 1. Notice in the table here, I wrote it as plus or minus 1. That's because this function f of x equals x squared plus 1. Squaring a negative gives you a positive. So plugging in both x equals positive 1 and x equals negative 1 gives the same output value here, or y value, 2. All right, now this by itself is not enough for us to understand what a limit is, which is this example is going to lead us to that. We have to gradually plug in more values of x that are getting closer and closer to 0. So from x equals 1, let's get a little bit closer to 0. Let's go with, let's say, 0.5. Plug that in, you'll get 1.25. Now, just to kind of build your quantitative skills, you should be able to do that calculation without a calculator. Think of 0.5 as 1 over 2. And if you plug 1 over 2 into this function, 1 over 2 squared gives you 1 over 4, a quarter. And then you add that to 1 in that function, you get 1 plus a quarter. Write that as a decimal, 1.25. All right. Well, still 0.5, a half isn't that close to 0. We can get closer. Let's go with, let's say, 0.25. Look at this value, 1.0625. We still want to get closer to 0 with our value for x. So let's go with 0.1, and let's get even closer. Let's go with x as 0.01. All right, now the concept of a limit requires plugging in multiple values. And we can kind of see something happening here. This is why the example is worded as examine the values of the function. Do you see anything happening with the function values, the y values, the right-hand column? Take a look at all those values. On the left, our x values are gradually getting closer to 0. Any guesses for what the right-hand column, those function values are approaching? Well, a reasonable guess, you can probably see it, would be 1. And for that reason, we're going to kind of give the notation for a limit before we define it, in case you're at all familiar with limits from a previous course in some context. But what we write here is we say that the function values approach 1 as x approaches 0. All right, we might write that symbolically as f of x approaches 1 in that arrow notation as x approaches 0. All right, and for this example, this is kind of motivating the idea of a limit. So in a little bit, when we define what the limit of a function is, we'll write this notation here. The limit as x approaches 0 of f of x, this function, equals 1. And that's because here we're seeing that the function values, or y values, are getting gradually closer to 1. One thing I want to point out before we move on is notice if we just take that function and plug in what x is approaching 0, we get f of 0 to be 1. So that's the same kind of function value as the limit value we found here, 1. All right, we'll kind of come back to that in a little bit, something about plugging in. All right, let's take a look at the graphical approach for the same example. So we have kind of, again, multiple ways to understand limits. The numerical approach is one option. The graphical approach is another. All right, so here, what we basically use is we start with the graph of the function, which for this one is rather simple, a parabola, and then the +1 shifts it up 1 unit. Now this is really the numerical approach. If you think back to that table of values, we have a table of x comma y values. Now, well, that's really what a graph is made out of, a bunch of ordered pairs, x comma y, and we just plot a lot of them. So this is really the numerical approach, we're just visualizing it with the graph of the function. All right, in the numerical approach, we let our x values gradually get closer to 0. And then we looked at what happened to the function values. The connection here is function values are y values. So when we let our values of x get closer to 0, notice they're kind of moving down the x-axis, going from 1, gradually getting closer to 0. Those x values correspond to points on the graph right above. So when we are using the graphical approach here, we basically follow along with the y or function values until we get close to the point on the graph with x coordinate here, 0. So you can see as we gradually get closer to 0, our function values are kind of going down that right side of the parabola towards the vertex. That vertex is at the point 0, 1. So we'd say here the function values or y values are approaching 1 as x approaches 0. All right, due to the symmetry in the graph, the same thing happens as we approach 0, but kind of from the left side. All right, so here we would summarize and say the y values approach 1 as x approaches 0. This is giving us another way to understand this limit statement. The limit as x approaches 0 of this function equals 1. Now, graphically, these function values are getting close to that point on the graph, 0, 1. All right, we'll make that connection between function values and limit values here. With this first example out of the way, let's now kind of give some definitions for limits. All right, so here we have kind of a standard form for a Calculus 1 definition of a limit. Starts to get a little technical. So there's a few things here. First, we're going to have f represent a function. And we want that function to basically be defined at all values in an interval containing a. A is going to be the x value that we're approaching. And we're going to allow for one exception. The function might not be defined at a. A is going to be the x value that we're getting closer to, like 0 in the previous example. But we might actually have the function being undefined at that point. All right? Here, capital L is going to denote a real number. We're going to use capital L to denote the limit value. And we have this definition that says if all or every function value approaches the real number L as the x values approach a, then we say L is the limit of that function as x approaches a. Now, I underlined it here because it's important. We have to have all the function values getting gradually closer to some number L. If all function values do that as x approaches a, we say L is the limit of that function as x approaches a. All right, so we would just write that here as f of x approaches L as x approaches a. Just to keep in mind, just to recall, coming out of your pre-calc course, function values are the same as y values. So we could write that alternatively as y approaches L as x approaches a. All right, so what this kind of definition is suggesting is if a function has a limit as x approaches a, then every single function value has to be getting closer to one number L. All right, let's just mention a few important things about that definition that are important for our purposes. So we'll give some important remarks regarding the limit of a function. All right, and we stated earlier that we actually don't care if the function is defined at a. All right, and that's because during this process of evaluating a limit or taking a limit as x approaches a, we never consider x equals a. We gradually get closer and closer to some number a, but we never actually care about reaching x equals a. All right, just kind of restating what we emphasized, but just to kind of make it official. All values of the function must approach that same real number L in order for the limit to exist. We're going to see some examples where certain values of the function approach one number, other values approach a different number. In that case, we would say the limit doesn't exist. We have to have that the function values approach a single number L as x approaches a. All right, now what the second comment or remark is kind of alluding to is we're going to see eventually that some limits do not exist. So we have to have every function value approaching the same real number L for the limit to exist. If the function value approaches two or more different function values, then the limit would not exist. We'll elaborate and build on that as we go with some further examples. All right, let's get to basically another example. This one, maybe make an attempt at it. So pause the video and give yourself an attempt. It's the same thing as our previous basic example using the numerical approach, but now it's just for a different function. So here the question is, use the numerical approach, plug in a lot of different x values, make a table, and we're going to use that table of function values to guess the value of this limit. The limit as x approaches 0 of e to the x minus 1 divided by x. If you feel comfortable with exponential functions, maybe pause the video and make an attempt. Otherwise, I'll wait a few seconds and you can just continue with me. All right, so this is our kind of first time encountering in our Calculus 1 course, the exponential function e to the x. just as a little brief review, hopefully you recall E, it's what we call Euler's number. It's a number kind of like pi. It has an infinite non-repeating decimal representation. Pi is approximately 3.14. Good number to just know. E is approximately 2.72. Here's a little more accurate decimal representation, 2.71828. All right, so just a brief review of that. When you're using your calculator for this example, make sure you use your calculator's built-in exponential value or the exponential function. Don't approximate, there could be significant rounding errors. All right, so what we're going to create in our table for the numerical approach is just a table of x values that are gradually getting closer to 0, and we're going to see if the y or function values seem to be getting closer to a single number. If they are, then that single number is basically what we define as the limit of the function. All right, let's do a value here that we can basically calculate, I hope, without a calculator. So let's plug in x equals 1. All right, notice this function has e to the x minus 1, and then an x in the denominator. If we plug in x is 1, we get e to the 1, or e, any number to the first power is itself. The numerator is going to be e minus 1, and then plugging in x is 1 in the denominator as well, we just get division by 1. So here, we get the exact function value, or output, e minus 1, and we can just easily approximate that, provided you know a decimal representation for e, about 2.71828, and just subtract 1 from that. This is about 1.71828. All right, pretty much every other value for x that we're going to plug in beyond here. Again, we want our x values to gradually get closer to 0. So 1 isn't that close to 0. We can get a little closer. You're probably going to want to use your calculator. I myself have no real quick way to calculate exponential values. So let's pick a value for x that's closer to 0. Let's go with 0.5. And if you plug that in, you'll get 1.29 and then a bunch of decimals. All right, we plug in a different value for x that's getting closer to 0. Let's go with 0.1. And then we will gradually get closer and closer to 0, plugging in x as 0.01. And then finally in our table here, 0.001. All right, that's just plugging in. Definitely use your calculator to get these function values. And what we can notice in that right-hand column, it seems that all the function or y values are gradually getting closer. Any guesses? Long dramatic pause. Looks like they're getting closer to 1. And that is the value that I was hoping you would guess. So we're going to say here that the value for this limit, we're guessing it here from this table. This doesn't mathematically prove it, but we're going to guess that the limit is 1. And as it turns out, a little bit beyond where we are right now in our course, it actually is correct, mathematically true, that this limit as x approaches 0 of e to the x minus 1 divided by x is 1. All right, we see that in the table, all those y or function values gradually get closer to a single number, 1. All right, now this one's a little different than our first basic example. We try to plug in here, well, just notice that factor of x in the denominator, plug in x is 0, you get division by 0. So we don't get the same function value as the limit value 1 here. All right, now this example is multi-purpose. It works for a second example on the numerical approach, but it's a good example to compare with our first one to see what's going on with plugging in. And what I'm going to kind of say right now, but not give you the complete truth yet. We're going to wait a little bit till we have some more ideas developed in our course. But right now, I'll just point out that plugging in doesn't always work. If we think back to our first example, where the function was x squared plus 1, we saw that the limit as x approaches 0 was 1. All right, if we plug in x equals 0, we get 1. All right, so that seems to work there. The function value and the limit value work out. They're the same. Now that doesn't happen in what we just encountered with example 1. From our table, we guessed that the limit correctly as x approaches 0 was 1. Something happens when you plug in x equals 0 to this function. It's not quite undefined like you would be thinking from algebra when you have pure division by 0, or in other words, a number divided by 0. Something's going on here. Notice what happens when you plug in x equals 0. You do get 0 in the denominator, but since e to the 0, any number to the 0 power is 1, our numerator becomes 1 minus 1, which is also 0. So we get this peculiar quantity. It's not quite undefined, but similar. It's something called an indeterminate form. That's something that we'll be going into detail on within the next lecture. But here, this is enough to see plugging in doesn't work here. 0 over 0, anytime you have a least division by 0, something mathematically is going wrong. All right, so maybe you're thinking, how do I know when plugging in works? How do I know when it doesn't? We'll save that for later when we're kind of ready. All right, let's get to the next part of this first lecture. We're going to kind of jump to a related topic called one-sided limits. The examples we were looking at so far as x approached 0 in those two examples, we basically did so from kind of values that were a little bit bigger and a little bit less than 0 simultaneously. So the previous limits, we might call them a limit or two-sided limit. What we're going to be looking at now is the idea of what's called a one-sided limit. All right, so let's jump straight to an example. I don't want to give a definition. Let's motivate it with a concrete example. So here, we're going to use the numerical approach, again, to guess the value of this limit. The limit as x approaches 0 of x divided by absolute value of x. I'd like you to pause the video and give an attempt at this. We'll check in about a minute. Something's going on here. All right, welcome back. So we're going to use the numerical approach. Since we probably don't know what the graph of x divided by absolute value of x looks like. As it turns out, being able to sketch a graph, or what's called in calculus curve sketching, that's actually a long-term goal of ours. So we don't know the graph here. Let's try the numerical approach. Seems pretty straightforward. Let's start by plugging in some positive values for x that gradually get closer to 0. All right, and this actually isn't that bad because every single value for x that you plug in, 1, 0.5, 0.1, 0.01, we get for our output or function value here, 1. Notice why that is. When x is positive, absolute value of a positive number is just that number. So this function is basically then a number divided by itself. A number divided by itself always cancels to 1. All right, so not hard to see here. As x approaches 0 from positive values to the right of 0, it seems that the y or function values approach 1. In fact, they are always equal to 1. All right, so you might guess here that the limit is 1, positive 1. Well, let's see what happens if we approach 0, but through negative values for x. Negative values for x compared to 0, they're just to the left of 0. All right, now something different happens. Think of what happens with absolute value of a negative number. Like, for instance, absolute value of -5, you get +5. So it basically kind of eliminates the sign, the negative sign. But the numerator here has an x in it. That's what's going to make all these function values now come out to be -1. So be careful, when x is negative, absolute value of x doesn't necessarily cancel to x. It cancels to the positive version. So here, when x is negative, x divided by absolute value of x actually cancels to -1. All right, so through now the negative values of x that gradually get closer to 0, that table is seeming to suggest that the limit as x approaches 0, those function values are getting closer to -1. Now there's an immediate problem. We stated in our definition that if a function has a limit, all function or y values have to approach a single real number. And what we see here, some of the function values approach +1. These other function values approach -1. We're going to conclude here that this limit doesn't exist. But this example actually motivates what is called one-sided limits. All right, so we're going to say here, as x approaches 0 from the right, to the right of 0 are all the positive values, the function value approached +1. Now we're going to write it in a kind of limit notation down there. And notice the addition of a little positive sign. It looks to be up in the exponent. That's going to denote the direction that we're approaching from with a one-sided limit. So here, kind of think values to the right of 0, those are all positive values. That's where the notation comes from. So here, from the right, this limit approached +1. All right, something happens differently when we let the values of x approach 0, but now from the left, those are the negative values of x. We find that the function value is approaching -1. And since the function values are approaching two different numbers, that's enough for us to conclude that the limit here does not exist. So we'll typically write that here. We'll say the limit, we'll write DNE, abbreviating does not exist. All right, now again, the point of this example was to introduce limits from the right and limits from the left here. But this example, again, is multi-purpose. It gives us a connection between one-sided limits as x approaches 0 from the right, the positive values, or as x approaches 0 from the left, negative values, and the relationship to limits or two-sided limits. All right, so let's get into what that relationship is. So first, let's kind of introduce individual one-sided limits. So this is really just notation. It's still the concept of letting x approach a number, but now we're just approaching from one side. So what we're going to call here a limit from the right, we're going to approach a, but only from values to the right of it. To the right of a number, those are bigger values. So we'll be plugging in here values of x that are greater than a. All right, a limit from the left is pretty much the same thing. We approach a number a, but now from one side. And now to the left of a, those are values that are less than a for x. So we would plug in a value for x that's less than a when kind of thinking of or evaluating a limit from the left. All right, notice the notation, and notation is important once you hit calculus kind of and beyond. We denote a limit from the right or left just with a little sign in what looks to be the exponent, but it's just notation, just how we denote a limit from the right with a little plus or a limit from the left with a little minus. All right, now at the top here, it's listed as important, but this is just notation. It's not really that important. What is important is this third comment or remark, the relationship between one-sided limits and limits. Earlier, think back to our first example, we let x approach 0 from both sides, positive and negative values, simultaneously. So sometimes we'll just call limits that limits. If we need to emphasize, we'll call a limit a two-sided limit. So there's a difference here between the one-sided limits and a two-sided limit. Now the relationship between those two related concepts stated here as a kind of an important theorem. And it says that if the two-sided limit of a function as x approaches a equals L, that happens if and only if the individual one-sided limits to that same value for x, a, but now either from the right or left, equal the same number, L, for the limit value. All right, so what this is saying is if a limit exists, a two-sided limit exists, it must be the case that the individual one-sided limits both exist and are equal. All right, now earlier we were mentioning something about the possibility for limits to not exist. Our previous example we were just looking at that introduced one-sided limits with the function x divided by absolute value for x. Well, we actually saw there that the limit does not exist. Now, the individual one-sided limits do exist. In example 2, we saw the limit to the right, or from the right of 0, was positive 1. The limit from the left, or to the left of 0, was negative 1. So individually, the one-sided limits both exist, but they're different. This is going to happen somewhat frequently. Why does the two-sided limit not exist here as x approaches 0? Because the individual one-sided limits are not equal. If your one-sided limits to a point A are different, then the two-sided limit does not exist. All right, and that's something that we will build on immediately after this in part 2 of this lecture, where we'll jump straight to another example dealing with kind of a graphical interpretation for one-sided limits.